everyone, welcome to the third day of my DSA tutorial series. I would like to introduce today's topic by asking one question. Have you ever wondered how GPS finds the shortest route? Even some roads have delays and are closed. So today we are diving into the Bellman-Ford Algorithm, a powerful pathfinding algorithm that can handle negative weights and even detect when there's no valid shortest path. I'm Subodha, and by the end of this video, you will understand how this works exactly. So let's get started. Bellman-Ford is named after Richard Bellman and Lester Ford, who developed it in 1950s. It's like the reliable backup plan when things get complicated. I will explain more about the Bellman-Ford algorithm. So look at this graph. What Bellman-Ford algorithm do is find the shortest path from source to all vertices for weighted graph with negative weight. So you might think the Dijkstra's algorithm did the same thing. Yes, it finds the shortest path from source to all vertices for weighted graph. But what it can't do is, it can't calculate the negative weights. So the specialty of Bellman-Ford algorithm is, it even calculates the negative weight graph. So let's discuss why we need the Bellman-Ford algorithm. Bellman-Ford algorithm can handle negative weights and detect negative cycle, and it also tells us when there's no solution except. The main purpose of the Bellman-Ford algorithm is find the shortest path from a source vertex to all other vertices in a weighted graph. Now let me explain the core concept of Bellman-Ford algorithm. It's something called edge relaxation. So this is the heart of how the algorithm works. Watch this animation carefully. The initial state is, we start with three vertices A, B and C. A is our source. Notice it green with distance 0. B and C start at infinity because we haven't found the path yet. So look at the edges. A to B cost 5 and A to C cost 10 and B to C cost 3. So let's look at step by step. Step 1 is first relaxation A to B. The calculation is distance A plus weight. So distance A is 0, weight is 5, so total is 5. Is 5 is less than infinity? Yes. So we update the B from infinity to 5. So this is relaxation. We found a better path, so we update the distance. See how B lights up and changes from infinity to 5. Step 2. Second relaxation is A to C. The calculation is 0 plus 10. It means 10. So 10 is less than infinity. So we update the C from infinity to 10. So step 3. The third relaxation. This is the important one. So relaxation B to C. So current distance to C is 10 from going directly A to C. But what if we go to B instead? Calculation is distance B plus weight. So distance B is 5. We calculated it before. Weight is 3. So solution is 8. Is 8 is less than 10? Yes. So see how C's distance changes from 10 to 8. It is old distance get crossed out, the new distance disappear. So we found a better path. Going A to B and B to C, total 8 is better than A to C total 10. So this is the power of relaxation. Okay, now we know Dijkstra's algorithm fails with negative weights. But how does Bellman-Ford algorithm actually handle them? Let me show you with a real example. Let's go through these steps. Look at this graph. We have 4 cities A, B, C and D. Most would have normal costs 4, 2 and 3, but there are one special road from C to D with weight -5. Let's see how it works. So we started vertex A with distance 0. All other are infinity because we haven't found the path yet. First check edge A to B weight 4. So current distance to A is 0, edge weight is 4. New distance to B equal to 0 plus 4 means 4. Is 4 is less than infinity? Yes. So update the B from infinity to 4. We found a path. Next we check edge A to C. Current distance to A is 0, edge weight is 2. New distance to C equal to 0 plus 2, that means 2, and 2 is less than infinity, so we update the C from infinity to 2. Next we check edge B to D. Current distance of B is 4 and the weight is 3. So new distance to D equal to 4 plus 3. So it equal to 7. 7 is less than infinity. So we update D from infinity to 7. Next we check the edge C to D. Now here's where it gets interesting. The edge from C to D with weight -5. Current distance to C is 2 and edge weight is -5. It is negative. So new distance to D equal to 2 plus -5. It means -3. Wait, is -3 less than 7? Yes. -3 is actually better than 7. This is the key. Even though -3 sound negative and weird, it means we found a cheaper path. Update D from 7 to -3. I will explain why Bellman-Ford works with negative weights. So here's the key insight. Bellman-Ford doesn't care if edge weights are positive or negative. It just asks one simple question. Is distance from plus weight less than the distance 2? If we guess update, it works the same way whether the weight is +5 or -5. That's why Bellman-Ford handles negative weights. It's not afraid of negative numbers in its comparisons. Okay, now we have seen how Bellman-Ford finds shortest path with negative weights. But what happens if there's a negative cycle? This is where things get really interesting. Let me show an example graph with 3 vertices A, B and C. So look at this. A to B weight is 1, positive number, and B to C weight is 2, it is also a positive number, and C to A weight is -4, it is negative number. So this is the key. Now let's see what happens when we run Bellman-Ford on this graph. So let's work through step by step. Step 0, that means initial state, we start with our source, that means A, 0, the green node, so B and C are infinity. Let's begin this algorithm. In the iteration 1, first we relax edge A to B. The calculation is 1 and it is less than infinity, so we update B infinity to 1. Next we relax edge B to C. Calculation is 1 plus 2 equal to 3. So 3 is less than infinity. So we update C infinity to 3. It is still normal. So it's C to A. This is critical. Now watch this H carefully. C back to A with weight -4. The calculation is 3 plus -4. It is -1. So -1 is less than 0. We have to update the A from 0 to -1. So A was our source. It was 0 and now it is -1. This is our first clue something is wrong. By going around the cycle A to B, B to C and C to A, we found a better path back to where we started. So let's go to the iteration 2. We start again with H, A to B. Now A is -1 now, so -1 plus 1 means 0. So we update B from 1 to 0. So next we move on to the HB to C. B is now 0. So B plus 2 is 2. We update the C from 3 to 2. H C to A. C is 2 now. So 2 plus -4 equal to -2. So we update the A from -1 to -2. It got even more negative. Then you can see the pattern. Every time we go around the cycle, the distance keeps getting smaller and smaller. Normally Bellman-Ford does V minus 1 iteration. V means vertices. So for 3 vertices, there is 2 iterations. If we can still relax an edge after V minus 1 iteration, it means we have negative cycle. Every time we go around the cycle, we subtract 1 from our total distance. Go around once, -1, go around twice, -2, go around 3 times, -3. We can keep looping forever, making the path infinitely negative. This means there's no shortest path. You can always find a shorter one by going around the cycle one more time. I think now you have an idea about what is Bellman-Ford algorithm is and how it works, and what is negative weight mean, how Bellman-Ford algorithm handle it, all the things. So if this video helpful, please like on this video and subscribe to our channel. See you in the next video. Until then, happy learning.